Transistors are one of the most significant inventions in modern electronics, revolutionizing the way we design and use electronic circuits. They are semiconductor devices that control electrical signals, acting as switches or amplifiers. Since their invention in the mid-20th century, transistors have played a crucial role in technological advancements, leading to the development of computers, communication systems, and numerous electronic applications. Before the invention of transistors, vacuum tubes were used for signal amplification and switching in electronic circuits. However, vacuum tubes were bulky, consumed a lot of power, and had a limited lifespan. The breakthrough came in 1947 when John Bardeen, William Shockley, and Walter Brattain at Bell Labs invented the first working transistor. This innovation led to the rapid miniaturization and efficiency improvement of electronic devices, paving the way for the digital revolution. Types of transistors. Transistors come in various types, each suited for specific applications. The two main types are 1. Bipolar junction transistors, BJTs. BJTs consist of 3 layers of semiconductor material, forming either an NPN or PNP structure. 1. They have 3 terminals: the emitter, base, and collector. 1. BJTs are widely used in amplification and switching applications. 2. Field effect transistors, FETs. FETs operate using an electric field to control current flow. 2. The two main subtypes are metal oxide semiconductor field effect transistors, MOSFETs, commonly used in digital circuits and microprocessors due to their low power consumption and high switching speed. Junction field effect transistors, JFETs, used in high impedance applications, such as amplifiers and sensors. Applications of transistors. Transistors have a vast range of applications, including 1. Computing. The microprocessors and memory chips in computers rely on millions, or even billions, of transistors to perform complex calculations and store data. 2. Communication systems. Transistors are used in radio transmitters, cell phones, and fiber optic networks to modulate and amplify signals. 3. Power electronics. High-power transistors control electrical energy in devices like motor drivers, power supplies, and electric vehicles. 4. Medical devices. From hearing aids to MRI scanners, transistors enable precise signal processing in medical equipment. 5. Consumer electronics. TVs, smartphones, and gaming consoles all rely on transistors for efficient operation. The impact of Moore's law, proposed by Gordon Moore in 1965, predicts that the number of transistors on an integrated circuit doubles approximately every 2 years, leading to exponential growth in computing power. This prediction has largely held true, enabling the development of increasingly powerful and compact electronic devices. However, as transistor sizes approach atomic scales, new challenges such as quantum effects and heat dissipation arise, prompting research into alternative technologies like quantum computing and graphene-based transistors. The future of transistors. As technology progresses, researchers are exploring new materials and techniques to further improve transistor performance. Some of the emerging trends include 1. Nanotechnology. Carbon nanotubes and graphene transistors offer potential solutions for overcoming the limitations of traditional silicon transistors. 2. Spintronics. Utilizing the electron's spin rather than its charge could lead to more energy-efficient computing systems. 3. Quantum transistors. Quantum computing relies on quantum transistors to perform calculations at unprecedented speeds. Transistors have shaped the modern world, driving advancements in computing, communication, and numerous other fields. Their continued evolution will define the next generation of technology, ensuring that electronics become even faster, smaller, and more energy efficient. As researchers push the boundaries of materials science and quantum mechanics, the transistor's legacy as a cornerstone of modern electronics will undoubtedly endure.